Well, next let's talk about the Riemann sum. We use the Riemann sum to estimate the area under the curve. So let's say you are given a curve, look like this. And you want to calculate the area under the curve from A to B. And so you go ahead and divide this into x sub n interval. And you're looking at the rectangle under the curve. You try to add up the area under the rectangle of the curve. Now, note that here, when we add up the area, part of the area being negative, right? So here the area so the Riemann sum is only talk about it, add up the area, the overall area, the displacement, if we would say that the area under the curve is that much. It doesn't account for the total area. So there are two different things. The Riemann sum only looking for the area under the curve and add them all up, whether it's positive, negative part, or it cancel out. The Riemann sum area can be 0. But when you talk about the total area of under the curve, then that's going to be positive. Now let's see how do we use Riemann sum in order to calculate the area under the curve. Now, note that each of these rectangle under the curve, each of this rectangle is of the width of the rectangle, delta x, is equal b minus a divided by the number of the rectangle that you're looking at, right? And here, the length of the rectangle, whatever this value is, we call this x sub I star. Then the length of each rectangle is f of x sub I star. This meant the area under the curve is just the area under the curve can be estimated by using the Riemann sum, right, with x sub I, because here we have the area of the rectangle, that is length times width, okay, and estimate to n of them. Now, if we let n approaches infinity, we divide the area, each of those interval to be as small as possible and let the number of rectangle go to infinity, then the limit at n approaches infinity of the Riemann sum will give you the area underneath the curve. Let's see how that would work. First, we want to find the Riemann sum for f of x equal x squared minus 6x using the right endpoint, and we have from the interval from 0 to 3 for n equals 6. So first of all, let's take a look at what is our delta x. Delta x is equal to 3 minus 0 divided by 6, that equal to 1/2. Okay. So the each of x sub I on the interval from 0 to 3 and we divide this to 6 interval. Okay. This is x sub I. Each of x sub I is equal to the starting point plus 1/2. Because this is our right endpoint. So if you want to use the left endpoint, so right endpoint, make a note. X sub I equal the starting point plus delta x. Left endpoint, x sub I, the first x sub I is equal to the starting point, the next one, x sub 1, x sub 1, x sub 2, then equal to a plus delta x. Okay, so now that we have our width and our endpoint, we can write our Riemann sum at n equals as I equals sid, I equal 1 and n at sid because we have sid rectangle of f from x sub I equal to delta x times k, delta x times I, okay, I times delta x I. So we look at 1/2 k times 1/2. So this is 1/2 times the sum of I equal 1 to sid of 1/2, and we want to use I, 1/2 I squared minus sid times 1/2 I, and this is our Riemann sum. We expand this out, multiply it, we get this is negative 20 over 8. This is negative 10, negative 5 over 2. So note that the Riemann sum here is negative. So what happens if we go ahead and evaluate this for as n approaches infinity? And x squared minus sid x here. Okay. So we're looking at delta x is equal to 3 minus 0 divided by n. That is 3 over n. And because we want to use the right endpoint, this is x sub I equal 0 plus delta x times I, that equal to 3 over n times I. So we look at the limit, the estimate area equal to the limit at n approaches infinity of the summation of I equal 1 to n of f of 3 over n I times 3 over n. So this is the limit at n approaches infinity of the summation of I equal 1 to n of 3 over n I square minus sid times 3 over n I we will go ahead and simplify the inside. We go ahead and we simplify this part. So this part is become the limit at n approaches infinity of negative 36n squared minus 27n plus 9 divided by 2n squared, and this equal to negative 18. So the area approaches negative 18. Suppose you are sitting on the bank of a tidal river, watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour. With the result shown in the table, how far upstream did the bottle travel during that hour? Find an estimate using 12 subintervals of length 5. With part A, we want to use the left endpoint value, and part B, we want to use the right endpoint value. Okay. We know that the distance equal the rate times the time. So part A, the distance equal the rate times the time. Well, if we want to use the time equal to the left endpoint, we look at first we look, the rate is 1 times 0 plus 1.2 times 5 using 12 intervals. So then we look at 0, 5, 10, 15, 20, 25, 30, 35, 40, 45. So these are our left endpoint. Okay. So far, so on, plus 1.2 times 55. And this telling us that the distance is equal to 475. In part B, again, if we want to use the right endpoint, then our first starting point is 5. So D equal 5 times 1.25, 1.2. Plus 10 times 1.7, so on and so forth. The last one is 60 times 0, and this distance is 475. So it's saying that in so you're sitting there and watching the bottle traveling up the stream in a total of 475 meter in 60 seconds, in 60 minutes. Okay, so that now, before I move on, I do want to stress the importance of figuring out the right endpoint and the left endpoint of your Riemann sum. You need to be very careful of what are the points that you are using. Otherwise, you run in something you can't really solve or something that's even harder than what you should have. So make sure when you use this type of Riemann sum, making sure you know what is your right endpoint and what is your left endpoint and how to find them. Okay.